Hello, welcome to third CAD session of Engineering Design and Practice module. In today's session, we are going to talk about CAD assemblies, rendering, and we will also make an introduction to technical drawings. Before we make the start, let's briefly talk about the CAD assignment requirements. So this assignment is going to be worth 15% of the module. And there are three main requirements to the assignment. So the first one, you need to make all CAD models in SolidWorks to complete the Stirling engine assembly model. So once you complete all your parts and assembly, you need to produce a photorealistic rendering of the assembled model. And also you need to create a technical assembly drawing of your Stirling engine, including the full part list. Second requirement is to design a flywheel. So your flywheel design must meet the following specifications. So you should assign the material. It is going to be an aluminum alloy. And you have already provided a design template which would effectively be your design space. So you should maintain the outer diameter, the overall width, and the inner diameter of the template model. So using that template model, you need to systematically remove material to achieve the mass and moment of inertia target. And finally, the third requirement is to create a number of part drawings. So you need to create drawings following the BS 8888 standard. So the drawings that you need to complete according to the standard is top plate drawing, bottom plate, column, and piston cylinder. So these are already given as examples. So you should make your own drawings, not to replicate the ones that already provided. And finally, you should create a drawing for your own flywheel design, showing also the mass and moment of inertia values on the drawing. You must ensure that your drawings are suitably dimensioned and toleranced. So you need to make an electronic submission. All you need to do just to submit a zip file containing 5 PDF technical drawings of the components, 1 PDF of the assembly drawing, a colored image of the photorealistic rendering you created, and all the CAD files, so all the native SolidWorks files. In this table, you can see the weighting of different aspects of the CAD assignment. So if you look at the first row, you would see that the part drawings are taking 50% of the final grade for the assignment. So you should be careful with understanding and paying attention to drawing rules. So when we are discussing, so what we are going to be looking at the drawings, fundamentally, they should adhere to the standard. And we will also look at the overall layout, how you use the views, how you use dimensions, clarity of your drawings. And you must also ensure that you use the provided template, which you can find in Model CAD tab. And also, you need to create an assembly drawing, which would take 10% of your final grade. And similar to the part drawing, you must ensure you follow the standard rules, and you should include a part list, appropriately use balloons to identify the components and clearly show the assembly details with suitable views. Your flywheel design would only take 5%. You must ensure that your design meets specification. You should come up with a sensible design. You must ensure that your part can be physically made using any sensible manufacturing method that would make sense to you. And you should also ensure that you come up with a original and aesthetic design. As similar to the flywheel design, rendering takes only 5%. So we will look at the overall quality of the rendering, the choice of view, and the overall appearance of the model. Part files, so those would be your 3D SolidWorks part files, would take 20%. So we are going to be looking at the features used in creating parts. So what type of features you used, if you have used any advanced features that we discussed in the second session. You should also ensure that you correctly fully define and dimension your parts using smart dimensions and geometric relations. Finally, the assembly file would take 10%. You must ensure that you suitably use assembly mates, and you must ensure that your model is either fully constrained or constrained so that it shows the correct motion of your model. Okay, let's have a look at today's learning objectives. So by end of this session, you will have understanding about how you can create assemblies from individual SolidWorks parts and how you define the interaction between those parts in an assembly using different assembly mates. We will look at different mate types. We will also review and will introduce you to a SolidWorks add-in to produce photorealistic renderings. We'll discuss about the orthographic projection methods. You'll understand the difference between the first and third angle projections. And then you should be able to look at the component and understand how it would be arranged in orthographic projection. This would help you to decide which views that you can add to the drawing to clearly show the details of your parts. And then we will discuss how you can organize and arrange clear technical drawings. And finally, we will discuss different line types commonly used in engineering drawings. Okay, let's start with the assemblies. So assemblies are effectively the collection of parts in a single model. So in general, there are two different assembly approaches can be mentioned in CAD. The top-down approach, basically you make the parts within an assembly. So you first decide for the higher level system and then you break that system down to individual components. The other approach is called bottom-up approach. So in this one, you first create the parts individually, then put them together into an assembly model. So for now, we will only use a bottom-up approach as the parts have already been made. We will use the pressure relief valve as an example. So we will come to that shortly. But let's review the assembly environment in SolidWorks. So similar to the parts, you can create an assembly using the new document option. But instead of selecting part, you should select assembly at this stage. And then once you created an assembly, the environment or user interface would be pretty much similar to the parts, but there would be some different toolbars. So the first one would be the assembly toolbar. This is the one we would mostly be using. So here you can find different commands or different actions that you can do in your assembly model. So you should understand the typical process involves when an assembly model is created. So the first step is to start a new assembly file, and then we insert the first part. So we basically start with the existing parts in the bottom-up approach. So we should have them before we attempt creating an assembly file. So once you are in a new assembly, you insert your first part. And by default, it comes in a fixed position wherever you drop on the assembly model. And then you insert another part. Then you assign mates between the parts to impose the movement restrictions on them. So we will elaborate that shortly. But effectively, these mates are pretty much similar to the assembly sketch dimensions and relations. But instead of using all these geometrical relations at sketch level, we just use them at assembly level between the parts. And ideally, all of your parts in the assembly should be fully constrained, unless you want to show the movement for an animation. Okay, let's have a look at a few important points before we attempt making our first assembly model. So effectively, a new assembly file can be created directly or be made from an open part and assembly. So we can start an assembly file similar to the parts, just start in a new document and select an assembly and open it. Or if we have an existing part, we can directly start making an assembly from that part file. And similar to the parts, each assembly file contains an origin and 3 standard plates. In addition to that, you can also see a mates folder. So every time you add a mate to your assembly model, they will be stored under mates folder. So components can be added in several different ways. So you can simply drag and drop them from an open part window, or you can open from a standard browser. So we will look at those methods shortly. Once you add your first component, that would be automatically fixed in the design space. So when a component is fixed, you can't move it in the design space. So as your first component is fixed, then you can keep adding the other components and define the geometric relationship between the second or third component and the first one. So we said that the first component comes in fixed state, but that's typically arbitrarily fixed in a random position. So we would also want to control the position of the first component in the assembly file. So in this point, it would be good to remind that it's a good practice to add a coincident mate between the origin of the first component and the assembly. Again, when we are making the first task, we will look at how we can do this. And also, we need to understand the unit system in an assembly file can be different from the unit system in the part files. For example, you can assemble a part made in inch system and a part made in millimeter system, and assembly can use completely different units. So let's review the mates in SolidWorks assemblies. As we said earlier, mates in SolidWorks work similar to the sketch constraints. So there are three main mate types. The standard ones, they're almost identical to the sketch constraints. So we have coincident mate, parallel mate, perpendicular mate, tangent mate, and a few other simple mates. And there are also two other categories. The second one is advanced. So under advanced mates, you can find symmetric, path, coupler, and many other advanced mate types. And the final category is mechanical mates, where you can define mechanical-like relations between the components. So you can use cam, slot, hinge, gear type mates. But most of the assembly models are using standard mates. And when you are using standard mates, you would often to be creative in the way you apply the mates. So you can use offsets rather than coincident or parallel. Or you can use axis points or other geometries of the parts. And you can also use mates approximately position your parts. Standard mates are the most common ones that we would be using in assemblies. So we can use different objects in standard mates. We can use faces, edges, or vertices of a geometry, or we can use sketch lines and points from the part model. And similarly, we can use part planes, axes, or origins to mate. The most mates are made between a pair of objects. So we can select a face from a part and another face, edge, or vertex from the other part. Then that would create a pair for a mate. So two most commonly used mates are coincident and concentric. So the cylindrical components, we would mostly be using concentric, and almost all the other type of geometric relations can be used coincident mates. Obviously, there would be some occasions where we would need to use the other mate types. One type of mate that you can find in the standard mate list is lock mate. So you should avoid using lock mate. It works similar to the fixed relation in sketch constraints. So it basically arbitrarily fixes the component in the space, or you can lock two components together to move together. But in this case, it doesn't define a geometric relationship between components. So it just locks the component at the position that you selected locking, but you can't control the geometric relation once you use lockmate. So you should avoid using lockmate at all. Okay, let's have a look at the SolidWorks assembly tree. So in part models, so this tree is typically where we see our list of features. But once we start inserting parts to our assembly model, we would see all those parts under this list. And as we said earlier, there is also a folder for mates. So let's have a look at the different symbols that we can see in the assembly tree and what do they mean. So the first one, we said when we insert our initial component, it comes in fixed state. So each part name, you would see an F in brackets. That means the component is fixed. So you can't move, you can't drag, you can't rotate the component with respect to assembly, planes and origin if a component is fixed. The second one is floating type components. So if a component is floating, you would see a dash in brackets. So here is an example on the assembly tree. So the second component is at floating state. So you can move the component or rotate it with respect to other components or the assembly, planes and origin. So effectively, floating components are underdefined components or under constrained components. So there are some freedom of movement within the assembly. And if you see nothing next to the part name, or if it's blank, you don't see anything, that means the component is fully defined within the assembly. So we would like to see this type of components in SolidWorks assemblies. So we try to avoid fixed components or floating components. So we want them to be fully constrained. And once a component is fully constrained and you try to add more mates to define its position, therefore you will try to overdefine the component position, and then you would see this red arrow with a plus sign in bracket that would show in the error in that component. So you must ensure that you resolve this issue and bring the component back to the fully defined stage. So ideally, all paths should be fully defined unless you want movement of the component. So we said that first part comes in fixed state. So we need to resolve that first. To do that, we need to right click on the component and select float. And then we should expand the component features and select the part origin and the assembly origin and add a coincident mate to fully define the position of the first component in the assembly. And for larger assemblies, it's useful to create different sub-assemblies first. So we have an example. So this is the example of the pressure relief valve that we are going to be completing today. So here what we see, a number of components. It's showing a cross-section view of the complete assembly, and then we have balloons attached to each component with different numbers, and then we have a very simple part list showing the part number in the balloons and a part description. So by now you should have most of the components to complete this assembly exercise. So you should have all the parts listed here. If you haven't done these components yet, just go back to the first and second session slides and find the relevant part drawings and complete the drawings and save them. So once you have all these parts, you can start creating this assembly. But notice that we have 14 items in the part list, but we only have 8 or 9 components in this list. So we are missing some of the items. So let's have a look at them. So we are missing item 5, which is a compression spring, and springs are typically standard parts. So they are off-the-shelf standard components. Item 7 is a lock nut, and similar to that, it's a standard component. 9 is a pin. Again, the pins are made to standard size and lengths. Item 12 is an O-ring, and item 13 is another O-ring. So as you see here, this is the 12 and this is 13. And again, all the O-rings are standard off-the-shelf components. So we're missing the standard parts, but we have all the other custom-made components to complete the assembly. So let's have a look how we can get those missing parts. So effectively, we use an add-in in SolidWorks called Toolbox. So Toolbox effectively a library of standard parts that is fully integrated with SolidWorks. So once a Toolbox add-in is active, you can find various standards, and then you can select the standard, let's say ISO standard, and then under each standard folder you would see different part types. So those are the standard parts that are made to the selected standard. So you can find bolts, nuts, retaining rings, keys, O-rings, pins made to the ISO standard. And similarly, you can find similar components for British, German, or American standards. So to use Toolbox, all we need to do, just browse to the component that we want to add into the assembly and drag and drop that component. Then for added component, you can adjust its size. So whatever the key size parameters that you want to control, let's say for a bolt, it can be the diameter and length, and similarly for an O-ring, it can be inner diameter and cross-sectional diameter. So you can control those parameters to adjust the size of the component. Okay, here is our first task to do today. So we will start creating a sub-assembly. So as we said earlier, we can break complex assemblies down to the different sub-assemblies. So here is what we are going to be doing here. For the pressure relief valve assembly, we will be creating a sub-assembly which would be called sealing adapter. So in this assembly, you can find the item 1, which is sealing adapter, and item 3, the adjuster screw from your part list. The other items, so item 2, which is a circlip. In this case, it is going to be an external circlip. So item 4, metric 10 nut, as you see here. And item 5 is an O-ring. So you can find those 3 items from the toolbox. Okay, let's start with creating an assembly and with the other first steps that you need to be aware of. So we said we could create a few different ways of assemblies. So the first one is directly selecting a new assembly document type. So let's do that. Once we click on the assembly, similar to the parts, it would open an assembly. And typically by default, SolidWorks will show these begin assembly properties where it would bring this open window, and then you can navigate to your first part file that you want to insert. So let's use the first item here and then click open. So now we have option here to drop that part to anywhere that we want. So let's just drop it somewhere. So as we said, the first part comes with the fixed state, as we see here. But let's understand where it's fixed in the assembly first. So what I'm going to do, I will just make 3 main planes visible. So let me just make sure that we can see the planes. Here we go. So, and also let's show the origin as well. Okay, so here is the assembly origin with the 3 main planes in the assembly. So effectively the intersection point of those planes. And then we have the part origin. So we can expand the part tree and see the number of features used in this part. And then let's also show the 3 main planes of the part. So you see it's located somewhere away from the assembly origin. And let's just insert another one, or just insert second component, and then you see we have many options to locate the first component. So we can simply drag it at a place, and you see this comes in floating state. So we don't want this situation to be happen. So we want our first component to be located with respect to the assembly origin, and then we will locate the following components with respect to the first one. So let's use that approach and let's see how we can fix that issue. So our first item is this item 1, valve body, and it's in fixed state. So what we need to do here, just right click on the component and select float. Once it's in floating state, we can move the component. Let's just go back to the fixed state, just right click on the part and select fixed. And now if I try to drag and drop, well, it's just moving the plane representation, but if I actually try to select the component, it says selected component fixed and it cannot be moved. So let's resolve that. Just right click on the component and select float. And now we will use mates. So effectively mates, they create geometric relations between the components and to define allowable direction of linear or rotational motion of the components. Here is the definition of mates given by SolidWorks. So let's add our first mate. We will select the mate, and here we have mate selections. So let's expand the assembly tree from the graphical area. Let's select the assembly origin and expand the first component and then select the part origin. So once we do those selection, SolidWorks will suggest the best mate types for the selections we just made. So it picks up a coincident mate and aligning the axis. So whatever the X, Y, Z axis in the part will be aligned to X, Y, Z axis of the assembly. So in a simple term, the front planes would be coincident, right planes would be coincident, and top planes would be coincident between the part and assembly. And once we click OK, and let's click OK one more time to close the mate properties, and we would see that there is no fixed or floating sign next to the part name. That means this part is now fixed. So I'll just hide the planes so that you can see what's happening, and I'll also hide the origins. So now the first component is fully defined, and when I try to drag and drop this component, it gives me a message on the screen saying the selected component is fully defined and it cannot be moved. But I'll try to drag and drop the second component, which is in floating state, so I'm free to do that. So I can rotate the assembly and move the component, or if I just right click and hold on a face of a floating component, so I can just rotate it. So it's just rotating the component. I'm not rotating my view of angle, just rotating the component with respect to the assembly planes and origin or any other fixed components in the assembly. So this is not manipulating the view. This is actually rotating the component in the design space. Okay, so based on that, let's just go back to our first task and create the ceiling adapter subassembly. Okay, let's open the first component, which would be the ceiling adapter. So I have saved all the parts under a folder called pressure relief valve parts. So the first one is sealing adapter. So this is item 2, and I'll just open this component so that I can show you another way of creating assemblies from a part. So typically, if you created this part in older version, you would see this warning here. So there is nothing to worry about. All you need to do, just click save, and that would convert the older version file to the version that you are using. So let's resolve that issue first. So see how we can create an assembly from a part. So if you have a part open, then we can go to new document drop down, and then we have option here says make assembly from a part or assembly. So we can use that, or we can go to files and then make assembly from part option. So either of these choices would give you the same result. So let's use this one. So we have sealing adapter listed under open documents box, and then if we just click OK, what it will do, it will bring the first component in fixed state, but at this time the part origin and the assembly origin are coincident, and all the planes are also mated. But we don't have all these mates in the model yet. So if we use make assembly from a part method, we bring the component in the correct position that we want to do, but there is no mate or anything defined. So let's do that. Let's just right click on the component and select float. So let's use mate command and then select the assembly origin and then expand the part tree and select the part origin. So just make sure coincident mate is selected and align axis option is checked. So you might have noticed the part hasn't moved because it was already in the right place, but all we did is just add the coincident mate to control its position. Okay, so this is the first step that we want to do. So let's add the second component. Let's go to insert component and then browse. So navigate to the working directory and then let's add the item, which would be adjuster screw. So click OK, open, and then just drop it anywhere on the graphical area. Okay, the second component came in floating state as expected. So let's try to add different mates to make sure the component is fully defined. So let's see what we are doing here. So we are editing an assembly and this assembly is now undefined. Okay, so let's use mates, see what we can do. Let's select the mate. So what we want to do, basically bring this part into this hole here. So this cylindrical face and that whole face, once we select those with a mate command active, SolidWorks would suggest that we can add a concentric mate, which is pretty much what we are trying to do. So let's click OK. And let's click OK one more time to make sure we close the mate command. And see how we can move that component. So let's just click and hold on a face of this second component and try to move it. As you see, now it is concentric with the hole, but it's still free to slide along the axis. And also notice that it is still free to rotate around the center axis. So we need to look those degrees of freedom on the component to make sure it doesn't move and it says the component is fully defined. So looking at the section view in the slides, what we can see, this face of the adjuster screws comes in contact with, let's just zoom in, that face of the ceiling adapter. As you can see, it is quite difficult to see those faces, and especially if that component is already in approximately right position, we don't know where it is. So we need to see what's happening inside the part. There are a few methods to do that. If you just want to see the inside, we can right click on a component and make it transparent. So then we can see how these parts are interacting. But again, this might make us selection options a bit difficult. So let's just change this part to original view state. The other option that we can use here is section. So we can activate section view. You can find it on the heads up toolbar on the graphical area. So once you select section view, what you would have here to select the default plane from the assembly, or you can select a face, or you can select the planes from the child parts. So let's use the front plane, or if you want, we can use the top plane, or we can use right plane. But we want to use front plane in this example. So let's do that. I'll click OK. Then this will activate the section view. So it's basically permanently hiding the, it's basically temporarily hiding the other half of this assembly. So let's activate the mates and carefully select this face on the ceiling adapter and that face on the adjuster screw. So once those faces are selected, you would see that a coincident mate would be picked up by the software. So effectively, if we make two faces coincident, they would be in contact. So let's click OK to accept that, and let's click OK one more time to accept that. And then I'll just deactivate the section view. So let's try to drag and drop this component. Okay, so we have restricted the movement along the axis, but the rotation about the center axis is still free. So we need to rotate its rotation. So we need to lock its rotation. And there are a few options that we can use here. So the first we can use a planar face. So it can be a face on this screwdriver slot, and we can use any of these faces from the hexagonal shape of the ceiling adapter. So let's do that. Let's go to mates, select the planar face here, and let's select another planar face here. So once we made those selections, you would see that SolidWorks would make those two faces parallel. And let's click OK, and one more time, and you would see the adjuster screw is now fully defined. So as both components are fully defined, the overall assembly would also appear as fully defined. So this is just one way of locking rotation. So let's delete that mate and see what else we can do. So I'll expand the mates tree and would locate the mate that I want to delete. So this is the parallel mate I just created. And I'll right click on that and select delete. And I'll just confirm. So as you have noticed, the adjuster screw moved back to floating state. Okay, so it can still free to rotate. So the other option here, using the planes. So let's activate the mate tool again, and then expand the assembly. So let's carefully examine some of the planes. So we need to select a plane going through the center axis of the part. So just carefully looking at that. So let's look at this view orientation. So the front plane meets that criteria. So it goes through the center of the part. If you look at the top plane, it also does, but the right plane is basically perpendicular to the axis. So let's select the front plane and then expand the adjuster screw, and then we need to carefully select a plane that meets the same criteria. So it basically goes through the center axis of the part. So we can select again the front plane or top plane under the part planes. So let's select the front plane again, and here we can either make those coincident, or we can make them parallel, or we can make them perpendicular. So either way, we will lock the rotation. So let's select the coincident and click OK. So in this case, we have control on the orientation of this slot. And the last method could be, let's just delete that last mate I just added. I'll just confirm that delete, and then the part is again at floating state, underdefined. So the third method could be directly locking the concentric mate. So let's just right click on it and select lock rotation. So in that case, you would see that the concentric circle is now filled. The inner circle in the concentric mate icon is now filled. That means the concentric mate has locked rotation state. So we can just right click on that again and make it unlocked. And honestly, this is my least preferred method, because if you are working with a large number of components and using locked concentric mate, you may have issues with controlling the part positions occasionally. So I would prefer mating two planes. So let's go back to mate, expand the tree, select the front plane, and then front plane of the part, and make them concentric. Or if you'd like to orient the slot vertically, so you can use perpendicular command. So this completes the first step. So we have created the assembly using the two custom parts. So let's just save it. I would save that as ceiling adapter subassembly. So that would be the file name that I'll be using, and we'll save it. Okay, so let's add the other components. So from the part list, we've seen that the other components are just standard parts. So we have a nut, we have an O-ring, and a circlip. So let's add those components to the assembly. And we said that for those components, we can use toolbox. So to activate toolbox, there are a few methods that we can use. So the first one is go to tools and then scroll down to the bottom and then find add-ins. Or alternatively, you can expand the options drop down and go to add-ins. And here you would see a number of different add-ins available in the SolidWorks installation. So what I want to use is SolidWorks Toolbox library. So just make sure you select the first column to activate it and click OK. So once you have made this selection, now Toolbox is active. So where we can find the Toolbox components. So on the right hand side of the SolidWorks window, we have a set of menus which is called task pane. So in the task pane, we can find different tabs. So the second one is design library, and in the design library tab we have a toolbox option. So let's select that and I'll expand the tree, and we can use different standards. So the first item that I'll be adding is the circlip. So the circlip is made to PS 3873 standard. So I'll go to the PSI library and then we'll find the retaining rings, and then we'll go to external, and we only have one type of circlip under this category. So I will carefully rotate my component so that I can see the circular face where the circlip is going to be attached. So what I'm going to do, will click and hold on that part and drag and drop it to that circular face. So once we release the mouse button, you would see that the part is automatically added there with a size. Let's just make sure that we use the correct size. So from the shaft diameter drop down, this is the only parameter that we can change in this model. We can select different sizes. So by default, SolidWorks will select the closest matching size. So in this case, we will be using 4mm diameter. So let's click OK. And then cancel the insert component option. And you would see that the part symbol of a toolbox component is different than the normal part files. Just also notice that this circlip is now underdefined. We need to make sure that we fully define the component. See what mates we have associated with the circlip. So by default, SolidWorks added a concentric mate. So it's going to be basically two circular faces between the face we dropped component and a reference face from the circlip, and then a coincident mate is effectively a planar face of the circlip and a planar face on the groove. So all we need to do just to lock the rotation. So we can again use the planes to do that. I'll just zoom out to make sure that I can clearly see the planes of the circlip. So I can use plane 1 or 3. And similarly, I can use front and top plane from the assembly. So let's do that. I'll go to mates and then select the front plane. And from the external circlips, I'll select plane 3. And click OK one more time. And now the circlip is fully defined. So let's add the other components. So I'll just go back to BSI library and now go into the nuts folder. So I'm looking for a hex nut, and that hex nut is going to be, so we can look at different standards here. So as that drawing you have on the slide is referring to the old standard, which is equivalent of hex nut grade C. So you can simply zoom in to this end where we are going to drop the hex nut and select the hex nut grade C, and then just drop that onto that cylindrical face of the adjust screw, and it picks up metric 10. That's the size we want to use. Just click OK to confirm, and then if you want we can add more of those to different positions, but we don't want that, so I'll just cancel the insert component option. And let's have a look at what mates are associated with this lock nut. So at this time SolidWorks only added a concentric mate. So what we are going to do, we'll just add the other mates. So the bottom face of the nut is sitting on this top face of the adapter. So we just made those two. And we will again select the front plane of the assembly, and then from the hex nut I'll just rotate the part so that I can see the planes when I move my mouse over the part 3. So that's going to be plane 3 again. So we make this to lock the rotation of the nut in the assembly, and I'll click OK to twice. So finally, I want to add the O-ring. So my assembly is still fully defined, but the O-ring groove is not visible. So what I'm going to do, I will just select the ceiling adapter and hide the component. So this is where I'm going to be adding the O-ring. And we'll go back to BSI library and select the O-ring. And we'll go to all O-ring subfolder, and we only have one O-ring type. So I'll just zoom into the O-ring groove and carefully drag and drop the component. So the O-ring size is 3.6. See if I can make it a bit smaller. Yeah, so 3.5. That fits much better. And if you actually look at the part number given on the drawing, it starts with this reference number. So it's 0031-16. So that 31 refers to inside diameter, and -16 defines the cross-sectional thickness. And then I will click OK. We'll cancel the insert component again. And let's see what happens here. Let's just check the mates. We have a concentric mate, but at this time, as there is no cylindrical face on the O-ring, because it is a donut type shape or torus-like geometry, so there is an axis in this part, and SolidWorks added a concentric mate between the axis of the center axis of the O-ring and the cylindrical face that I dropped part onto. So as you would expect, the part is still free to rotate, and it might be difficult to see, but it is also free to rotate around its axis. So it's free to move along the center axis, and it's free to rotate around the center axis. So let's just add a couple of more mates to make sure it's fully defined. So here what we are going to be using an advanced mate. So let's carefully investigate the planes on the O-ring part, and we see that the top plane is going through the component, so going through the center of the component. So we can use that. Let's go to the mate, and this time we will use an advanced mate. So let's expand the advanced mate options and select the symmetric. So we need to select the symmetry plane. The symmetry plane is going to be the center plane, which is the top plane of the O-ring. And then we need to select two entities to make. So those two entities would be the planar side faces of the O-ring groove. So let's just select those two. So the center plane of the O-ring would be symmetry plane of those two faces. So effectively, it would locate the O-ring in the center of the groove. And I'll click OK. And I'll click OK one more time. So to see, now I can't slide the O-ring along the center axis. But it still can rotate about the axis, although we can't see it because of the topology we have here. So just notice the orientation of the front plane now, and I will rotate the component a bit and check the orientation. So just a bit more rotation. So let's do that. Just rotate a bit more, and you see how orientation changes. So let's lock that. So we can simply lock the rotation, or we can again use one of the planes of the O-ring to control its angular orientation. So let's do that. We'll go to mates again, and then let's use front plane of the O-ring and front plane of the assembly, and let's make them coincident. And I'll click OK one more time, and you see now the O-ring is fully defined. So I'll just right click on the ceiling adapter and we'll select Show Component, and I'll just zoom out so that I can see the assembly. So let's check the section view, how it looks like. So the section view through the front plane, and you would see that you would see some interference between the ceiling adapter and O-ring, and also adjust the screw and O-ring. So this is quite normal for O-rings because they are elastomer and they are flexible geometries. So once they're assembled in place, they will actually be squeezed to take the form of the groove. So if you have this interface for an O-ring, you don't need to worry about that. It is quite normal for O-ring modeling. So I'll just zoom out and examine the other areas of the assembly. And again, here we have an interference. So that's basically the screw or thread engagement we have between those two components and between the adjusted screw and nut. And similarly, you would see that the circlip is nicely located at the corner of the groove. So I'll just zoom out, press F key to fit my model to the screen, deactivate the section view, and save the component. After creating the sub-assembly of the ceiling adapter, now we are ready to create the complete assembly of the pressure relief valves. So we will just follow the same steps as we did in the ceiling adapter sub-assembly. Similarly, we will start with the main body of the assembly. So that part would be our fixed part. Then we will resolve that issue, make it floating, and mating the origin of the first part and the assembly. Then we will just add in more components or other sub-assemblies. So the one that we already created is ceiling adapter, to complete the exercise. So let's start with the item 1, which is the valve body, and use suitable mates to make this part fully defined, resolve the issue, resolve the fixed part issue, and then keep adding the other parts. So let's have a look at the assembly drawing. Okay, here is the section view of the assembly drawing. So we have already created the right hand side of the assembly. In a similar fashion, we can create the left hand side of the assembly. So what we have here, item 10 is control wheel, item 9 is a pin, So that would come from toolbox. Item 8 is control screw. Item 3 is adapter. Item 11 is control rod. Item 12 is an O-ring. That would be coming from toolbox. And we also need item 1. So on the left hand side, so item 3, 9, 10, 8, 11, so they can be created or they can form another subassembly. And then using the ceiling adapter subassembly on the right hand side and the other subassembly on the left hand side, you can create a top level with those two, starting with the item 1. So insert the valve body and resolve the fixed state, just make sure it's fully defined, and then bring the other subassemblies and bring the other components. So the only component that you wouldn't be able to find in the toolbox is item 5. So there is no compression spring under toolbox standard folders. So you can either leave that blank, or using the spring modeling method we discussed in the second session, you can create a spring model fitting inside the valve. Okay, let's start talking about the rendering. So if you remember from the second session, at the end of the session when we discovered applying different materials to the component, we noticed that when we apply a material to a part, the part appearance changes to reflect the material color or material finish type to show in the graphical area. So this view is only a basic or very simple representation of the material appearance, and it doesn't show off the design. So to make more attractive images, we use another SolidWorks add-in called PhotoView 360. And again, similar to Toolbox, this isn't enabled by default. So to enable it, you should go to the Add-ins window and select PhotoView 360. And once you edit PhotoView 360, you would see a new toolbar and menu items will appear on your SolidWorks screen. Sometimes the default material appearance or scene, the background color of your model don't produce the best rendering. So we need to be careful with that. We need to change the material appearance, or we need to change the scene, the background color, or any other the background scene that we want to apply to show off the design. So to change the material appearance, we use Edit Appearance button. So using the Edit Appearance, you can apply different colors or different finish types to the components or faces. And similarly, we can change the scene using Apply Scene button in the main view menu. So when producing photorealistic renderings, there are a few points that you need to remember. So the first thing is perspective. So when you add perspective to your model, you're not looking at your model using orthographic view angle or orthographic projection. So you apply perspective and your object will look more realistic. And also the choice of material will have huge impact on the overall appearance and quality of your rendering. The other point is the orientation, view orientation of your object. So you want to make sure that you choose the right angle that shows the most information about your design. So whatever the visual properties that you want to capture in that image, you must make sure you change your view angle. And also aesthetically, you must choose the most striking angle. And when you are doing your assignment rendering, you should ensure that you use perspective, you choose good material finish, and let's have a look at how we can create renders in SolidWorks. So the first thing to do is to activate PhotoView 360 add-in. So to do that, you should have a model open, either a part or an assembly. So in this example, I'm going to use the valve body part to demonstrate PhotoView 360 capabilities. So to activate add-in, you should go to SolidWorks add-in tabs if you have, and then select an add-in to activate. At this time we will use PhotoView 360, but there are different add-ins here. So we've used Toolbox. Similarly, you can use the other methods to activate an add-in. You can use options drop down to activate it, and alternatively you can go to tools and use add-ins to activate that. So the shortest way to use SolidWorks add-ins tab, and click on PhotoView 360. So after a short wait, you would see that a new tab would appear. It's called Render Tools. So let's switch to that tab. So here we have different commands that we can use when we are creating photorealistic renders. So the first one is editing the path or model appearance. So by default, this part has cast alloy steel material applied. So let's have a look at the display manager, and you would see that cast stainless steel finish is applied to the part. So we can edit this appearance. So once we click on edit appearance on the right hand side where the task pane is, you would see appearance scenes toolbar comes active. Here you can select different material finish, so you can select plastic, metal, or many other type of materials. So for steel, also for metals, there are different type of metals, and at each category and each subcategory there are different finishes that you can apply. So for steel, you can find polished steel, brushed steel, matte steel, or satin finish. You can find basic carbon steel appearance, cast stainless steel or cast carbon steel, or any other pattern or knurled finish that you can find here. or for aluminium, you can find similar finishes or different colors as well. So you can just look for the type of appearance that you would like to apply to your model, and simply you can either double click on it, or you can just drag and drop it to the part. So either way, you can apply this finish. So I'll just keep the default appearance as cast stainless steel. I'm not going to change this. And next step is to edit scene. So once you click on that, similarly, you can edit the background scene. So you can apply any studio scenes that you like to use. So just double click on that and you will see the background is changing. So let's use 3-point faded, simple white background. And we'll click OK. So once we are happy with the scene and appearance, next step is to activate the perspective. So from the heads up toolbar, if you expand the view settings drop down, you would see that perspective is not selected. So once you click on that, you would notice the perspective would be applied to your model. So when we are working with the CAD models, we don't want perspective to be active. So we just want to look at model from orthographic projection point of views. But for renderings, to produce more realistic results, we want perspective to be enabled. So once it's enabled, then we can click on either integrated preview, where your graphical area would be your preview screen to see how your render would look like, or you can use preview window. I'll select preview window, and after a short wait you would see your preview window will come up. So you can make changes on your SolidWorks model. So you can rotate the view and then come back to your preview window and see how it changes. So you can simply move its position, rotate it to ensure that you have an attractive view angle. So once you are happy with the preview, so you just check it and make sure the shading is applied nicely. So once you're happy with the preview, you would apply, you would start producing the final rendered image. So this is just preview, not final quality. So let's do that. So at this stage, you need to click on Final Render button. And once you click that, you would see another window will open. So that would show you your final render processing. So you would see that software is ENGR4003 is producing the final render. So this might take some time to complete. It depends on the quality settings you have in the final render or complexity of the model. once it's done, you can see the total time to complete this rendering task. So it's nearly 7 minutes. You can also zoom in to see if you are happy with the overall quality. So if you're not, you can go back to your SolidWorks screen and make the changes and create final render again. So once you're happy with your result, you can save the image. You choose a good rendering angle. Everything that we have covered so far was in 3D. So we discussed SolidWorks parts, assemblies, and renderings. So they were all representing 3D geometries. So now we will start talking about technical drawing. So the remaining of this session and the next session, our main focus will be technical drawings. So let's have a look at why the drawings are important. So effectively, we use drawings to communicate ideas with others. So you can think this like music. So a piece of music can be communicated in many different ways. However, to allow someone else to play the music, the musicians should use standard notation to communicate. So if they all use the same standard notation, even complex pieces can easily be understood. So drawings are very similar. They can effectively be taught as a visual language to communicate between engineers and designers. So we can only communicate the ideas effectively if we follow the rules. The other point about the engineering drawing is they must ensure that information is interpreted in the way it was intended. So standards must be followed. And it doesn't matter how the drawing is created. If it's created by a CAD package or by hand, it must follow certain standards. So not following the rules or being ambiguous can lead catastrophic failures. We can simply create drawings in SolidWorks from 3D models. So we can have part drawings, we can have assembly drawings from existing geometries. So this is fairly simple process, but there are a number of difficulties here. So the most challenging bit is to ensure that drawing follows the correct standard. And in fact, it's a generic rule that can be said about drawings. So all drawings, whether produced by hand or by CAD, must follow the correct standard. And whatever the standard we are following, all drawings should include similar type of information. So in a drawing, all dimensions should be included to clearly size all the features, and we must also show the relevant tolerancing. We must ensure that we use the correct line types, We should show all the relevant information in the title block. So whatever the information or additional information that we need to share. And we should also use correct projection symbol. Within the UK, BS 8888 standard is generally followed, and this is a sort of index standard for collection of different relevant ISO standards. So there are many more standards which are referred within BS 8888. So for example, there are at least 6 separate standards that refer to lines and terminators, and similarly 6 separate standards that refer lettering, and at least 18 standards that refer to representation of components. So as said earlier, it's sort of indexing standard using many other ISO standards as. So how you can access the British Standards online library? If you follow the steps in this and next few slides, you can simply obtain a copy of BS 8888. So all you need to do, go to Brooks library link provided here and click on find a database link, then browse our database by subject, select engineering and click on go. Then you can scroll down to find British Standards online and click on it. And then click on connect to British Standards online. That's where you need to log in with your university username and password if required. And then you will enter the British Standards online website. You would be logged in with your Brooks credentials. So then you can make a search for BS 8888. And then you would see a list of versions would appear on the search results. Whatever the latest version is, it could be 2017 or 2020. You can download a PDF of the standard. So we said that drawings are 2D representation of 3D components. So in a drawing, we need to provide a complete picture of a three-dimensional object on a flat sheet. To do that, engineers or architects use a means of communication known as orthographic projection. So let's take this object as an example and see how we can create views with different orthographic projection methods. So you can imagine the path placed between your eye and the horizon. The view you see is called an orthographic projection. So that's without perspective. So all you would see on a projected view is the outline or border edges of the features of the part that you are looking at. So the part can be described using a 3D sketch, which would normally be an isometric view, or series of orthographic views showing top front, left or right views. Essentially, we use two different projection methods when we are creating views. So these are first and third angle projection. So let's have a look at how we can create views in first and third angle projection and what are they actually meaning in engineering. So let's imagine two glass sheets that intersect in this image. So we have different quadrants in this arrangement. So we can just use different angle quadrants, starting with the first angle and rotating anti-clockwise. There would be a second angle and third angle and fourth angle. So in general, the first and third angle are used. Second and fourth angles, they are, so these are never used in projection. So let's see how we can construct first angle projection. So we place the component in the first angle quadrant as seen in this view. So this is our first angle quadrant, and we place the component in this zone. And then we just take this quadrant in isolation and we add a third plane back of the part. And then we look at the component from different angles. So that's basically, we look normal to each plane and then draw on the planes what we see when we look from different angles. And then we remove the object from this coordinate system and then unfold the planes. And then separate the views. So in this way, you would see in each plane would be representing a different view angle. So you will see a front view, which can also be called front elevation. You would see a top view, which is a plan view, and then end view or side view, which is also known as end elevation. And constructing third angle projection views are pretty much similar. At this time, we insert the component, the third angle quadrant, and we ensure that topmost surface of the component pressed against the underside of the horizontal plane, and the frontmost face of the component, this small face here, press against the vertical plane. So this is effectively what we get. And then similarly, similar to first angle, we add the third plane and then look at the planes and component orthographically and draw on the planes what we see. So we project the outlines and image feature boundaries on the planes and then unfold the planes. So let's have a look at the difference between the first and third angle. So this is what we got from the first angle, and that is what we got from third angle. And as you would notice, the views are identical, but the arrangement of views different. It all depends on the which projection method that you choose to use. So this is the front view, and similarly that is front view. So that's plan view, and in third angle the plan view is here, and then end view or side view, and here it's just the same view is located on the other side of the front view. So it may sound confusing. We can simply define rules to remember that. So let's have a look at this part. So we are looking at the component from different view angles, and we can just use a letter to identify our view direction. So A is the front side of the part, so that would be the front view or our principal view in this case. And then we have a number of side views, top and bottom views, and then back views. So if the view of A is our principal view, then view of B, which is the top view of the part, so that's view from above is placed below. So in the first angle, the top view is placed at the bottom of the principal view. View of E, which would be the bottom view, so this view is placed above the principal view. So above is placed below, below is placed above. So view of C is one of the side views. So view from left is placed on the right. So view from left is placed on the right. And similarly, view of D is view from right is placed on the left. And the F, so that would be view from behind, is placed on either side as is convenient. So it could be either placed next to left view or right view. So that's first angle. And the third angle, we have the same views, but the arrangement is slightly different. So view of B, which is top view, so the view from above is placed above. So view from below is placed below. View from left is placed on the left. The view from right is placed on the right. And view from behind is placed on either side as is convenient. So there is a quote from a standard referred in BS 8888. So it says, in those cases where it is advantageous to position the views not according to the strict pattern of the first or the third angle projection method, the use of reference arrows method permits the various views to be freely positioned. So what does that mean? Let's say if we don't have space to position the top view, let's say in third angle projection. So we say that view from above should be placed above. But if we don't have space in the sheet and we want to position it elsewhere, so we can use reference arrows to indicate that view. So that's indicating the view direction B, and then that is view B is just positioned next to it. And similarly, the bottom view is just positioned here. So normally in third angle it should be positioned at the bottom, or in the first angle it should be positioned at the top. And here similarly, the view of D should normally be on either side of the main view, But if there is no space for that, it can be placed elsewhere using reference arrows. So which projection method to use should be indicated in the drawing. So if you are using first angle, we use this symbol, and if we use third angle, we use that symbol. If we actually carefully look at the projection symbol, it's showing a truncated cone, but in first angle projection, we have the cone that could be side view or end elevation of the cone, and then look from left is placed on the right, so that would be somewhat top view of the cone. And in the third angle projection, similarly, we have top view, and then view from left is placed on the left. So in SolidWorks, you can easily define which projection method your drawing would be using when you create one, and also you can use standard drawing blocks to insert one of the projection symbols. You have already been provided with a drawing template. In fact, you have been provided two different templates. So the one showing first angle projection, the other one is using third angle projection. So there are a few rules that you must always remember. So the layout of all technical drawings should either follow first or third angle. Do not mix them. So if you are using third angle in a drawing, you can't combine these first angle. The projection symbol should match the drawing. Again, if you are showing your drawing is in third angle, you can't create view layouts in first angle. And typically a complete product should follow the same convention. So ideally, when you're doing your Stirling engine drawings, you must either choose first angle or third angle. So it's not ideal to make some of the drawings in first and the others in third angle. It would be good to keep one method in all drawings. All details and edges should be aligned between views. If they don't, there is probably a mistake. So as it's projected from top right, top bottom right to left, you must ensure that the edges must align between the views. It's far more common to draw a plan view rather than a view from below. So you must ensure that you orient your part accordingly. You would remember the part planning methods we discussed in the second session. So the second step in these planning steps was to choose first sketching plane when you are making a part, and we said your choice would affect the part's orientation, so you must ensure that you have the correct first plane choice in your model. So you can stop the video here and try to find the answers if you can recall whether this symbol is first angle or third angle. And here is another example. So you can try to find out if this is first or third angle. So a quick hint here. So we see the top view, and top view is effectively the view from top and its position above, and the view from right is positioned on the right. The same part, but this time different arrangement. So the view from bottom is placed on top, and the view from left is placed on the right. So let's discuss different drawing layouts and line types. So the first thing we need to be careful with the drawing layout is the drawing scale. So we use scale to for the objects if they are too large to draw full size to a standard sheet, or smaller objects similarly can be drawn with enlargement to scale, ensure the clarity. So the large components can be scaled down, small components can be scaled up. So the whole purpose of that, to ensure the clarity, the choice of scale should be made by drawing a quick sketch of the size of the object beforehand on a scrap paper. The main point of the scale is basically utilize the sheet space effectively. So we must ensure that we don't overpopulate the sheet space, or we don't leave too much blank spaces. So we just use the right amount of the sheet space in the drawing. And when you create your views, you must also ensure that you leave sufficient room around each view for labels, dimensions, or any other annotations that you will be adding. Or if you are doing an assembly drawing, you would need space for parts list. So as required by the standard, the original drawing shall be made on the smallest sheet permitted, the necessary clarity and resolution. And there are different recommended scales in BS 8888 standard. It is ideal to use these scales where possible. However, in the latest version of the standard, there is a new statement about that. Effectively says it is recommended that these scales are used wherever possible. However, with the advent of the CAD systems and the ability to view drawings electronically at any size, the importance of using a standard range of scales has diminished. Where the recommended scales cannot be applied, intermediate scales may be selected. So when you are, let's say, enlarging your components, let's say you are making a very small part on A4 or A3 size sheet. So when you enlarged it to 2:1 scale, you may see that you still have plenty of blank space, and so you haven't utilized the drawing sheet effectively. And then the next recommended scale is 5:1. But in that case, if you use 5:1, your views may not fit to the sheet space or drawing boundaries. So in this case, you need to use an intermediate scale. So either 3:1, 4:1, 3:2, or any other scale that would make sense. And similarly, for the reduction scales, you can select any intermediate scales if you like. So here is the typical drawing layout. So that's the template you have been provided. So let's have a look at some key aspects of this drawing layout. So we have a page border. So whatever we draw must be within these boundaries. Part number and code must clearly be indicated. Projection symbol depends on the view angle view projection method that you are using. For the first or third angle must clearly be shown on the drawing. And also there is a column called title block here where you can find useful information about drawing, about legal owner, so that's typically the company, the date of issue, so when the drawing has been when the drawing was produced, identification number if applicable, sheet number, so if you're using multi-sheet that you can state here, the drawing title, which would typically be the part description or your part name, approval, if that's been approved by a senior engineer, creator, or whoever drew the drawing. You can also see checked by, so that's another box typically used, and also document type, whether it's an assembly, subassembly, or detail drawing, etc. So let's start discussing different line types. Effectively, in each line type has a particular meaning in the drawings, and there should be a clear distinction between them. So you can see narrow or white lines, or you can call thin or thick lines. You can see solid continuous lines, dash and dot type lines, and there are a few other type of lines. So on the model, you would see technical drawing notes PDF. So this document is effectively a collection of the information or the key information that you would be you would require when you are producing drawings. So if you have a look at the page 9 of the technical drawing notes, you can see the most common line types. Other than the solid continuous line, whether thick or thin, the most common line type is central lines in technical drawings. So this is dash dot type line. So we have a continuous short dash and then a dot. So center line are used to indicate centers of circles, axes of cylinders, cones, threads, and lines of symmetry. So they should extend slightly beyond the feature, and they're referencing, they should never stop at another edge. So here you can see we have a central line showing the part center, and you see that line is extended beyond the outer diameter, so which is the circular feature that we are indicating. And similarly, we have a slot type shape here, and you see the central line is again extended beyond the feature. We say central lines do not extend across the space between the adjacent views. So here is the example. We have the front view of the part and the side view. As you see, the central line is not extended from one view to the another one. The other commonly used line type is dash type line. It's used for representing the internal features of the components. So in the projection, we show the outline of the components, but anything that cannot be seen on the outside of the component can be represented using hidden details or dash type line. So you can check the technical drawing notes, page 12, for more details. So we will do a drawing exercise. This part was created in the second session. So if you have saved it, you can use it. If you haven't, it might be a good opportunity to make more practice in 3D modeling. So effectively, you see the isometric view of this part. So you must create this part in SolidWorks as 3D, and then we will create a drawing of this part using one of the templates provided. So you can find first angle and third angle templates on Moodle. So what we are going to be doing is insert three main views of the part. So we will insert front view, right side, and plan view. And then we will include all hidden details and central lines. We will ensure that projection symbol shown matches the layout of the views. And we also have the following slides for additional guidance. So the first step is to create a new drawing. So let's assume you have the part. At this time, you will create a drawing. And then if you have downloaded the Brooks templates from the Moodle and extracted them from the zip file, you can just browse the location where you saved them. So we will be using third angle projection, which is in general far more common method compared to first angle. So most of the time in the practices we will be using third angle, and I'm sure in your career you would mostly be using third angle projection method. So once you created a new drawing, you'll be prompted to select the sheet format. So we will select A4 Brooks third angle template. So the sheet template's background and title box are on a separate layer. So that can only be changed by right-clicking on the sheet in the menu and editing selecting edit sheet format. So we will have a look at how we can do that. So you would need to edit the sheet format to input information to title boxes. So you can input scales, name, date, description, or any other information that you want to add. So once you've clicked, once you have inputted all the information for the title blocks, you can exit the sheet format by clicking on the icon in the top right of the main view. So we will have a look at how we can do that shortly. Before adding any views, you can set up the sheet's projection and scale by right-clicking on the sheet in the tree and select properties. So just right-click on the sheet, select properties, and you'll see the sheet properties. And here you can adjust the default scale and the type of projection. So if you have selected the third angle projection, you must ensure that the default projection method in the drawing is third angle. On the right hand side of your SolidWorks window, we have a view palette. Once you click that, you can expand it, and from the drop down you can select your part that you would be using in the drawing. So this would be called test part. If you use different name, it would appear in the list, or you can just browse to any part or assembly. The other option, similar to the assembly, we can use make drawing from part. But yeah, once you have selected the part, you would see the default views which you can simply insert onto the drawing sheet by dragging. So we will decide on the main view. Let's start with the front. So we just drag and drop the front view, and then position it suitably on the drawing sheet, considering we will add a few more views. We must ensure that we have space for the other views. So by default, hidden edges are not visible. So we will change that. Just click on the view, and on the left hand side you would have the view properties. Here you can change the display style. So by default, hidden lines are not visible. So we will switch to this one, the second graphic on the display style, which would show the hidden details. So once you made this selection, you would see two dashed lines representing the silhouette of the holes on this location of the part. And then we will create additional views using the projected view command from the view layout. So we will select the view and then select the projected view. So in this way we can create a view from an existing one. From the annotation toolbar, you can use center mark and central lines to add different lines to represent the circular or cylindrical feature centers. So you should try to reproduce this drawing following the steps. So you can see the hidden lines and then different central lines and center marks. You must ensure you save this drawing. We will just carry on adding more information to this drawing in the fourth session. So just make sure you save this drawing and use in the next session. Another point that you would need to be aware of. So effectively, if you create this side view, you would notice there is a solid line here where representing the tangent edge. So this is basically the planar face turns to a circular face. So this is the blending edge of the circular and planar faces. So it's called tangent edge. It's good practice to make these tangent edges hidden. So to do that, you can right click on a view and then go to tangent edge and make sure tangent edge removed is selected. This completes everything in this session. as usual, there are some additional my SolidWorks videos about the topics we discussed in this session. You can see different assembly videos about bottom-up assembly modeling using standard mates, some advanced mates, use move and rotate component. So that would be very helpful when you locate your components when they're floating. So how to use exploded view, that's something we haven't discussed, but if you're interested in finding out more about how to create exploded views in assemblies and use them in assembly drawings, you can watch this video. There are a few additional utilities that you can use. So this is a tool use clearance detection and interference detection, so you can check the clearance and interference between components in an assembly model using these tools. And there are a few other videos about physical dynamics, then assembly modes. I would strongly recommend you to watch these videos as well. And finally, a sample assembly exercise video here that you can watch to see how an assembly can be created. Another video is about toolbox, how to use smart fasteners. Unfortunately, there is no video in my SolidWorks about PhotoView 360, but you can always refer to SolidWorks help page for features on PhotoView 360. So this is not a video, it's just a text and some images, but you can read that to learn more about rendering. And finally, the drawings. So how you can create drawings and how to show details in the drawings, how to use sheet formats and templates, how to use detailing, dimensions, and how to use log view or log sheet. So these last two videos are going to be very helpful to understand different working methods in technical drawings. And again, in addition to my SolidWorks videos, there are some step-by-step interactive tutorials. So from the getting started section, you can go through the lesson 2 assemblies and lesson 3 drawings. So these are just first steps in assemblies and drawings. And then from the basic techniques category, you can complete assembly mates, toolbox, and PhotoView 360 and appearances tutorial. So the learning objectives that we covered today, we discussed different assembly mates and how you can make assemblies from individual parts using bottom-up approach. So we discussed different mate types that can be used in assemblies. We covered the photorealistic rendering using PhotoView 360 add-in. We discussed the orthographic projection. So hopefully now you have better understanding about the first and third angle projection methods. And now you should be able to look at a component and understand how it would be arranged in orthographic projection, regardless of the projection method that we are using. And also you should be able to understand how technical drawings are arranged. We discussed the different line types. Hopefully you know the different line types, central line or hidden lines, how they're used and where they're used. But more importantly, you should have appreciation of why the technical drawings are important in engineering. So this concludes this session. Thank you very much, everyone.